So this lecture is going to go over the quantum model of the atom as we start to discuss more the electronic structure of the atom. So last time we discussed the Bohr model of the atom, and what we said was the Bohr model did some good things, but it has two pretty major limitations in that essentially it only works on one electron systems, either atoms, and it doesn't work on molecules. So we need to go back to a more sophisticated model. And what we're going to turn to is go back to a question. Earlier we discussed the physics of light, and we said one of the interesting things about light is it can be a wave and a particle. And so the question we need to ask is, if light can be both, can other things be both? Are there bits of matter that can actually act as waves? And sure enough, the answer is yes. And we can start off talking about some of the history. In 1929, Louis de Broglie wins the Nobel Prize in Physics for his discovery of the wave nature of electrons. So what we're starting to see is that the electron, actually we need to think about as a wave and not a particle. So some information about this, de Broglie came up with an equation. So this equation here is what's known as the de Broglie wavelength. And what it's really saying is he can describe the wave-like characteristics of any object, any piece of matter, he can describe the wave-like nature. Now, the wavelength here is different than what we've seen in a standing wave. Because it's of an object, the wavelength is sort of this two-dimensional or three-dimensional wavelength surrounding the object. So we have a radius, and the wavelength is still crest to crest coming across. And the key is, in this equation, which we won't have to use, but the important piece is the wavelength is inversely proportional to the mass. And why that's important is because as the mass of an object gets bigger and bigger, the wavelength gets smaller. And what that essentially means is most of the time, objects have a wavelength so small, it doesn't matter. Like a baseball, we don't care about what the wavelength is because it's so small in relation to the size of the object. But if you have a very, very small object, something on the size of an atom or smaller, like an electron, the mass is so small that the wavelength becomes big, and we have to treat that object like a wave. And so people started to do some experiments, and they did the double slit experiment. So if you remember the double slit, we can take a piece of metal or something, shine a light or some source through the double slit, and if it's a wave, the waves emanate out from there, and you get this interference pattern of light, dark, light, dark, light, dark, light, dark. And this is evidence that something is acting as a wave. And sure enough, when we do this with electrons, so here's electrons, or here's electrons pictured as a particle going through the double slit, what actually happens when you shine enough of them, we get the interference pattern. Again, showing that the electron is a wave. It's definitely a particle, but it's definitely a wave. And so if we want to build our more sophisticated model of the atom, we actually have to think about the electron as being a wave instead of a particle. And this is what's known as the quantum model of the atom. This is quantum mechanics. If you've ever heard about quantum mechanics, this is what it is. We are not going to do much of it. We're going to touch upon the results so we can apply them to the atom. But there are a couple points that we should go over. This is developed by really three players: Werner Heisenberg, Louis de Broglie, and Erwin Schrödinger. Schrödinger is widely credited as being the father of quantum mechanics. And this is all based on the theory that the electron is a wave. This is also known as wave mechanics or quantum mechanics, and specifically, it's treating the electron as a three-dimensional standing wave. And we'll come back to that point in a second. So if you go through the math of this quantum mechanics, what's going to happen is what we're going to end up with are probability distributions. And what this means is we're going to come up with a region of space, a three-dimensional shape. Within that region of space, we can find an electron, right? So instead of a simple thing where the electron's orbiting something, we're going to have a shape. and within that shape is the electron. Now, the Heisenberg uncertainty principle says, and this is developed by Heisenberg, one of the interesting things is we can never know both the location and the momentum of the electron. And this comes out of the math of the system, but in general what that means is we can either know where the electron is, but then we can't know where it's going, or we know where the electron's going, but then we can't know where it is. Now that's a little bit problematic for us because then how can we really describe an atom? So again, this brings us back to this idea that we're going to describe a region of space where the electron is going to be. Instead of a specific location, a region of space. We're going to treat the electron as an electron wave. So we have to think about the electron as being a wave instead of a particle. And when we talk about an orbital, and that word orbital comes from the Bohr model. The Bohr model says the electrons orbit the nucleus, and we kept that word, but instead of thinking about the electron floating around the nucleus, we're going to think about the electron as being an electron wave oriented around the nucleus. And each orbital is a unique solution to the wave equation. All right, we're not going to go through the math, but we'll show the results. Each orbital can describe 2 electrons. This is a really crucial point for us. Every orbital can hold 2 electrons and no more than 2 electrons. And every electron in the atom is characterized by 4 quantum numbers. All right. So let's come back to this idea of a standing wave, because this is a difficult thing to think about. And the easiest way to think about it is a guitar string. So this would be a one-dimensional standing wave, where we have 2 points. You pluck the guitar string, it's going to vibrate back and forth. If you keep those 2 points, there's a couple different ways that this guitar string can vibrate. And the simplest form, or the lowest energy form, would be this one, where you pluck and the string just goes up and down. But depending on how it vibrates, you can actually vibrate this wave, and so that you see here you have a node in the middle. Right? And so this is nodes. Remember, a node in a wave is a region where the amplitude is 0. So right here, this wave string comes back and hits 0. So that's a node. We can also have it go like this, where we have 1, 2, 3 crests, 1, 2, 3, 4 crests. So you can kind of think about these as each one of these is an electron. And the region of space where the string is vibrating would be where we could find the electron. So the lowest energy form, we might call this n equals 1, n equals 2, n equals 3, n equals 4, where n is just the energy level. The lowest energy is this one, where we have one big region of space. And then we have this one where we have sort of 2 regions of space. And what's weird to think about is the electron could be in here, it can be in here, but it can never be there. Right? And yet it's both places simultaneously. Here, the electron can be in any of these 3 regions, but it can never be here or here. And the same thing goes for the last one. The electron can never be at these nodes. So you have these various nodes in these various regions of space. Quantum numbers. So this is always a little bit confusing. So review this a few times, ask questions when you have them. Quantum numbers, first of all, are really letters. When you solve this wave equation, these quantum numbers come out of it. The first quantum number is what's known as the principal quantum number, and it gets the abbreviation lowercase n. This designates the energy level. So that's sort of what we were talking about with our strings. So n can be 1, 2, 3, 4, going on as high as you want to go. This also tells us the size of the orbital. So the bigger the value of n, the bigger the orbital, the further it is from the nucleus. And as the energy level increases, the number of nodes increases, just like we saw with the guitar strings. The next quantum number is what's known as the angular momentum quantum number, and this gets an abbreviation of a script, lowercase l. This is going to define the shape of the orbital. So our orbitals are going to have different shapes, but groups of orbitals will have the same shape. And L the value of L can differ depending on what n is. So L can be every value from 0 all the way up to n equals n minus 1. We know L better by its letter abbreviation, so S, P, D, and F. So if L is 0, we call it an s orbital. If L is 1, we call it a p orbital. If L is 2, it's a d orbital. If L is 3, it's an f orbital. And again, this defines our shape. So every s orbital in the universe has the same shape. Every p orbital has the same shape. D orbital and f orbital all have the same shapes. And finally, we have what's known as the magnetic quantum number. And this is a lowercase m subscript L. This is going to define the orientation of an orbital in space around the nucleus. And we'll talk about what that means in a second. This is an integer value, and it goes from negative L all the way to positive L. So again, this depends upon what L is, and L depends upon what N is. So there's 4 quantum numbers, and these three quantum numbers define an orbital. So every orbital will have a unique set of these 3 quantum numbers. Okay. Each electron is defined by 4 quantum numbers. So it would be these 3 and the magnetic spin quantum number. And with the magnetic spin quantum number, we often think about this as the electron is a negatively charged particle. So the simplest way of thinking about it is you can think about that electron spinning clockwise or counterclockwise. And depending on how it does that, it's going to create a magnetic field, either pointing up or pointing up or pointing down. Now, we often just think about this as being spin down or spin up. And we think about this as being a value of 1/2. So we often call this being negative 1/2 and this positive 1/2. Right? Those are just the values we assign to the spin values. The Pauli exclusion principle tells us that no 2 electrons can have the same 4 quantum numbers. So another way of phrasing that is that every orbital can hold 2 electrons, but those 2 electrons have to have opposite spin. So 3 orbitals to define, 3 quantum numbers to define an orbital, and 4 quantum numbers to define an electron. Within an orbital, you can have 2 electrons, but one must be spin up and one must be spin down. All right, let's look at some shapes and look at some orbitals. We'll start off with the lowest energy quantum number. And the lowest energy solution to the wave equation is what's known as the 1s orbital. So 1s, whenever you see this abbreviation, this type of nomenclature for an orbital, that 1 is your n value. The letter is your L value. Okay, so 1s. Every s orbital has the same shape, and that shape is a sphere. So you can think of S standing for sphere. Now, the way these orbitals work is we can never know the location and the momentum of an electron. So if you could imagine, we could measure the location of an electron millions of times. And say, here, the nucleus is in the middle, here's the electron, here's the electron, here's the electron, here's the electron, and do it again and again and again. What you start to get is this probability distribution. And that's really what the orbital is. It's saying we have a 99% chance of finding the electron in this 3-dimensional region of space. So every s orbital is a sphere centered on the nucleus. All right, so that's what the s orbital looks like. Now, there's more than one s orbital. We can have a 1s. We could go up in quantum number and have a 2s or 3s. And what's going to be different between the 1s, the 2s, and the 3s are a couple different things. First, we can see the size. As the principal quantum number goes from 1 to 2 to 3, the orbitals get bigger and bigger and bigger. So a 3s is bigger than a 2s, which is bigger than a 1s. The second thing that happens is we start having nodes. So as n increases, the number of nodes increases. And anytime there's a node, you switch phase or sign of your wave function, which is what the color coding is trying to show. And what that is saying, if you think about a simple curve, if you have a wave, if here's my wave, and here's your sort of 0 x-axis in here, you can see we are negative amplitude, node, positive amplitude, node, negative amplitude, node, positive amplitude, node. So anytime you cross a node, you switch positive to negative. So your 2s orbital would have a small bit here, a node, and then a big bit. And then the 3s is small bit, middle bit, big bit with a node in between. And so what these plots down here are trying to show you is this is distance from the nucleus and the probability of finding an electron. So you can see with an s orbital, the highest probability of the 1s orbital being found is right here. It's the highest peak. And then it comes down and it levels out. And it never actually goes to 0. With a 2s orbital, there's a chance of finding the electron right next to the nucleus. And then there's a node. So you can never find the electron right here. And then there's the biggest chance of finding it way out here. And then it drops down. And then the 3s, it could be near the nucleus, a little further away, most likely here, but with 2 nodes along the way. So again, keys are s orbital is spherical. The bigger the quantum number, the bigger the orbital, and the more nodes. If we go to our next shaped orbital, L equals 1, this is a p orbital. Now if L equals 1, we look at our m sub L values. So m sub L is all values from negative L to positive L. So that means there's 3 possible values of m sub L. Negative 1, 0, 1. That means the p orbital, there's 3 orientations. So a p orbital is said to have a dumbbell-like shape. So here you can see this is what the p orbital looks like. And the 3 orientations are just different directions. So this orbital is going left, right, up, down, and this one's trying to go in and out of the screen. So a sphere you can only orient one way around a nucleus, so there's only one orientation. But at this dumbbell, there's 3 different ways we can orient that orbital. So all 3 of these orbitals have the same energy. They are degenerate. That's what this word means. They have the same energy, right? And they're all orthogonal to each other. In each case, there's a node, and the node is a plane that splits these 2 lobes in half, right at the nucleus. Right. So you should be able to draw the different 2p orbitals. There are 3 2p orbitals. You should be able to draw the general shape of these. All right. We could keep going and go L equals 2, the d orbitals. You don't need to know these, but I like to show them. So m sub L, there's 5 different orbitals, and here's what they look like. Here are your d orbitals. There's 5 d orbitals. They look like this. You don't need to know these. If you go on to take inorganic chemistry, then we'll talk more about them, and then you'll have to know them. There's f orbitals, L equals 3, and they start to look like this. 7 f orbitals, they start to get a little wild. You can keep going from there, but we'll stop at showing the orbitals now. So let's just think a little bit more about quantum numbers and orbitals. And we have this little table, but I'm going to take the time and switch and go to a note-taking app and kind of walk through this. What we want to do here is we want to assign all the orbitals in the first 3 shells, in the first 3 quantum numbers, n equals 1, n equals 2, and n equals 3. And the 2 things we want to keep in mind is each orbital is defined by a unique set of 3 quantum numbers, and each electron is defined by a unique set of 4 quantum numbers. So let's go through this together. And we'll start off with the first shell. In the first shell, n equals 1. So when we think about this first shell, n equals 1, that's our first energy level. If n equals 1, we can say, what does L equal? And one of the things to remember is L is going to be all values from 0 until we get to n minus 1. And then we can see m sub L is going to be equal to every value starting at negative L going to positive L. So in our example here, n equals 1, L is going to go start at 0 until we hit n minus 1. So 1 minus 1 is 0, so there's only one value of L possible. If L equals 0, our m sub L is going to go from negative L to positive L. And in this case, we only have 0, so the only possible value of m sub L is 0. So we have three quantum numbers here, three quantum numbers to define an orbital. So these three quantum numbers are the 1s orbital. So in the first shell, there is one orbital. The 1s orbital. And the first shell can hold 2 electrons. The reason I got 2 electrons is that each orbital can hold 2 electrons. We have one orbital, so that can hold 2 electrons, and those electrons would be 1 spin up, 1 spin down. We can go on and say, okay, let's look at the second shell and see how this is going to change things. So we have our second shell. So now n equals 2. So we're going to go through the same thing. We're going to say, what is L and what is m sub L here? So if L equals 2, L can be 0, and we're going to keep going with L until we get to n minus 1. So it can be 0, or I'm going to give myself some space, it can be 1. So now we have two possible values of L. We're going to treat each of those separately now and start off and say, if L equals 0, what is m sub L? And just like before, our m sub L would be 0. However, if L equals 1, then our m sub L is going to be all values from negative L to positive L. And so we have m sub L values of negative 1, 0, and 1. So what did we just find? What we're saying here, another way of thinking about this, is in the second shell, these three quantum numbers create the 2s orbital. But when L equals 1, this L equals 1 is a p orbital. So we can have n equals 2, L equals 1, and m sub L equals negative 1. That would be a 2p orbital. N equals 2, L equals 1, m sub L equals 0. That is a 2p orbital. And then we have 2, 1, and 1. That is a p orbital. So what we're really seeing is these are the 2p orbitals. And we can see there's 3 orbitals. So in the second shell, there are 4 orbitals. 2s, and then 2px, 2py, 2pz. 3 different p orbitals. And that can hold a total of, if you have 4 orbitals, each can hold 2 electrons, a total of 8 electrons. So we'll do one more. We're going to do the third shell. So we're going to start it the same way. N equals 3 now. So now we can say L is going to be all values starting at 0 until we hit N minus 1. So L can be 1, 0, 1, or 2. And then M sub L for each of those values. If L is 0, M sub L is 0. If L is 1, M sub L is negative 1, 0, and 1. And then if L is 2, M sub L is negative 2, negative 1, 0, 1, 2. And what are we seeing here? What do we have? We have the 3s orbital, 3p orbitals, and 3d orbitals. So there's 3 orbitals that are p's, and there are 5 orbitals that are d's. So we have a total in the third shell that gives us a total of 9 orbitals, which means this can hold 18 electrons. All right, so we're just walking through and figure out what are the possible orbitals in each shell. And this is also on our slides if it helps. It's all written out here. You can even take it to n equals 4 and follow and keep going with it. So our summary of quantum numbers, electrons are actually described as waves. If you solve the wave equation, you get 4 quantum numbers that define an electron, 3 quantum numbers to define an orbital, 4 to define an electron. The principal quantum number tells us the size and the energy level. The quantum number L tells us the shape, S, P, D, and F. M sub L tells us the orientation. It also tells us how many of that orbital there are. The M sub S tells us the spin of the electron. And what we're going to now start to do in the next lecture is to start to use these quantum numbers to determine the ground state of an atom and to describe all of the electrons by the orbitals that contain them. We'll look at that next time. Thank you.